Okay, this is lesson 3.7. Today we're looking at applications of derivatives. So we're going to be focusing on the natural and social sciences, and we're going to start with physics. So a really typical application of derivatives is looking at the position, the velocity, and the acceleration of an object. So in this particular example, we're given a position function. Sometimes in the textbook they use S for the position function. In this case, it's just labeled F. So the position function is a cubic equation, and it tells you where the particle is at any given time. And then so first thing we're going to do is graph this. Now on an assignment, I might ask you to graph it just because it's good practice to practice your graphing skills. On the test, I'd probably provide the graph for you just because I'm not specifically testing on if you can graph or not. So we'll just practice graphing here. This is a cubic function, which means the shape is going to look like this. Typically, I try to factor it to see if there's any zeros and go from there. So this one looks like it's easily factorable. We can take out a t, the t in every term, and then we'll see that it turns into a perfect square polynomial. So it factors to t minus 3 squared. So that means my zeros are going to be at 0 and 3. So I'll make a quick little table and we'll graph this out. So I'm also not going to consider any negative values for time because those are irrelevant in this example. So I know that one of the zeros is at 0. I know also that another 0 is at 3. And if you just plug in the x's into the function, I've already done that, so I'm just going to plop them in here. You can do that on your own if you like. Okay. And then I get 4. So that second 0 is a multiplicity 2. 4, and then, oops, and then 5, and then 20, and then we'll be off the charts after that. Okay, so let's plot this. So at t equals 1, it's going to be 4. T equals 2, it's going to be 2. 3, and then 4 is 4 again, and then 5 is all the way up to 20. Okay, so and this is a nice rounded function. Remember, we don't have any sharp corners in polynomials. I don't want to see your graphs having any V-looking things with a sharp corner, and then we'll just have an arrow there to say that it continues upwards. Okay, so that's a position graph. Now, what this says is that it never dips below 0, which means the particle is always in the positive side of wherever the 0 mark is. So if this particle is traveling left and right, it's always to the right of the 0 marker. So we can see it travels in the first second like 4 meters, and then it goes back another 4 meters, and then it goes 4 meters again, and then 20 meters. So that shows you where the particle is at any given time. Okay, now it says find the velocity at time t and graph it. So the velocity is always the derivative of the position function. So it's the rate and change of position. So it's how fast the position is changing over time. So take the derivative. So it's going to be a quadratic equation. So 3t squared minus 12t plus 9. And we want to graph this as well. This is a parabola, and it is easily factored. So typically I'll choose things for you that are easy to graph, just because, again, I'm not testing that. So pre-calculus 12 is 4 plus 3, and we can factor it to t minus 3, t plus 1. Oops, t minus 1. So there are 2 zeros in this quadratic equation at 3 and 1. So we'll graph them there, and then you can just make a quick table to plot the rest. So 3 and 1. I also know that y-intercept is 9. And then you can just plug in other x values to get the other ones. And I've already done that. So I can see at 2, it is negative 3. At 4, it is 9 again. And we have symmetry on a quadratic equation. So, and then we have 24, so it's like up here. So again, there's no sharp corners. It should be a rounded corner at the bottom. Okay, so there's our velocity graph. So I'm going to label them the position is velocity. Okay. Let's have a look at some of the other questions. When is the particle at rest? So we need to understand what that means. So when something is at rest, it's not moving. So when something's not moving, the velocity of that thing is 0. So we're just looking for where the velocity equals 0. Now, for that one then, you'll look at the velocity graph. And where it's 0 is going to be where it hits the x-axis. Where velocity graph hits x-axis. So these numbers along the y-axis here, those are telling you what the velocity is at any given time. So when you're at 0, that means you're going to have 0 velocity, means you're going to be at rest. So we can see this happens twice to the particle. So at 1 second and at 3 seconds, typically at these points, the particle would be like changing directions. Okay, so at t equals 1 and t equals 3. They didn't give us any units for this, so I don't know if it's seconds, hours, minutes. Sometimes you will be given units, and then you can add those in. When is the particle moving forward? So you can tell the direction that the particle is moving in by looking at the velocity graph. So the velocity can be positive or negative, and when the velocity is positive, that means that it's moving in the forward direction. When the velocity is negative, it means it's moving the downward direction or negative direction. Velocity is positive. So remember that all of these numbers on the y-axis here represent the different velocities at any given time for the particle. So all of these ones that I'm highlighting in yellow are all positive numbers. So when the graph is in the yellow zone, we have positive velocity. And when the graph is in the blue zone, we're going to have negative velocity. So from 0 to 1 second, the velocity is positive, which means that, so for example, at 0 seconds, it's 9. At half a second, it looks like it's 4. Which means that the particle is traveling in the forwards direction. Then from 1 to 3 seconds, it's negative, so it'd be traveling in the backwards direction or negative direction. And then again, it's positive after that. So you can write this in a number of different ways. I'll write it with bracket notation. So we'll say t is in, so from 0 to 1 second. We're going to use round brackets just because, like at the transition points, it's kind of neater. And t is in. Now, for the next region, it would be 3 and onwards. So we'll just say 3 to infinity. Okay. So I'm going to highlight yellow here so you can see. Okay, find the total distance traveled by the particle in the first 5 seconds. So when I'm talking about distance, direction doesn't matter. When we're talking about distances too, we're going to focus on the position graph. Okay, so I'm going to split it into certain parts. So I'm going to look at each sort of segment of the graph. So in this blue segment, the particle travels 4 meters. So it goes from 0 to 4. So I'm just going to write these numbers down below. And then in this green segment, it goes from 4 back down to 0. So that's another 4 meters. Remember, direction doesn't matter. So even though it was 4 meters in the negative direction, doesn't matter. And then in, what did it say, 4 seconds? First 5 seconds. And then in this next region here, particle traveled from 0 all the way to 20. And have 20. So in total, the particle traveled 28 meters, 4 up, 4 down, and then 20 up. Four plus 20, 28 meters, or whatever unit. They don't give us a unit here. Let's say 28. Determine the acceleration function for the particle. When is the particle speeding up and when is it slowing down? Okay, so that's an important one. Let's start with the acceleration function first. Now, the acceleration function is going to be the derivative of the velocity. So it's how fast the velocity is changing. So I'm going to write it over here, and then we're going to look at it together with the other graphs. So acceleration, a of t, would be the derivative of the velocity. I'm just noticing a typo here. I should have written v of t here. There we go. A of t would be 6t minus 12. Okay. If I were to graph that, I like to graph it just because it's a good visual for me. I'm a visual person. I like to see them. So that looks like it has a 0 at 2. 1, 2, 3, 5, 6. And it starts at -12. So the graph would look something like, so the acceleration is negative between 0 and 2 seconds. And then it's positive after 2 seconds. Now, when the acceleration and velocity are both positive, that means that you're going to have the particles speeding up. When they're both negative, the particles are also going to be speeding up. So let's have a look here and see what we can find. So in this first, I'll split it up into different zones. From 0 to 1 second, the velocity is positive and the acceleration is negative. That means it's slowing down. So let's record that down below. We'll split it into different zones. 0 to 1 second, velocity is positive, acceleration is negative, therefore it is slowing down. I'll write t equals, yeah. And I'm saying seconds here, we don't have units given to us, so I'm just using seconds as a default. It could be any unit of time. Okay, now let's look from 1 to 2 seconds. From 1 to 2 seconds, back up on my graph, my acceleration is negative and my velocity is negative. So they're both negative, meaning that they're both like going to work together and make the particle speed up in the negative direction. So velocity is negative and acceleration is negative. That means my particle is going to be speeding up. So when they're the same sign, you're going to be speeding up. Okay, now let's look at 2 to 3 seconds. So 2 to 3 seconds, my velocity is negative, I'm below the x-axis, and my acceleration has turned positive now. So they're different signs. Again, we're slowing down. B of t is negative, A of t is positive. Different signs means you slow down. And finally, for t is greater than 3, both are going to be positive, which means they're the same sign, they'll act together, the particle will be speeding up. Okay, there we go. So that's how you tell if a particle is speeding up or slowing down. You need to look at both the acceleration and the velocity, and when they're both the same sign, like they're both negative or they're both positive, you're going to have the particle speeding up. Okay, so that's kind of the physics example. All the physics examples will be pretty much the same. You'll be given graphs of the position, velocity, and acceleration, and then you have to answer questions about like when the particle is going in what direction, or how far it travels, or when it's speeding up or slowing down. Okay, the other type of example I want to go over today is in economics. We're going to learn some new terms. So this is on the next page. We'll talk about the cost function today. In later lessons, we'll also learn about revenue, but today we're just going to focus on cost. So C of X, when we're using an economics example, usually we're referring to some kind of production company where they are producing some units of a product or a commodity. And C of X would then represent the cost of that. Okay. Then this word marginal comes up. So marginal just means derivative or rate of change in. So C prime of X would be the derivative of the cost function. It just represents the rate of change in the cost when X items are being produced. So it basically means if you want to produce one more item, how much more is that going to cost you? And then if you were working for this company, you could use the marginal cost to make decisions about whether to increase production or decrease production. Okay, so let's do a practice. And by the way, you do have to know this word marginal and what it means. Okay, so a company estimates that its cost function is this. Find the cost of producing 500 items. Okay, so if we're just finding the cost, we just simply use the cost function. So this is not having to do calculus in this particular example. Just plugging in X is 500. So 10,000 plus 5 times 500 plus 0.01 times 500 squared is 15,000. Now we need to know the units for this. It's a word problem. So in this case, it would be dollars. So to produce, and we'll write it in the sentence, to produce 500 items, it costs $15,000. There we go. Okay, now for part B, it says the marginal cost is at 500 items. Write your answer in the sentence. So for this one, first we need to find the derivative before we can plug in the x. So the derivative is just 5 plus 0.02x. And now we're going to plug in 500. Oops. 5 plus 0.02, 500 is 15. Now we have to know the units. So remember, this is a rate of change. So it's the rate of change in cost, so dollars per item produced. So it essentially means, like, if you increase your, in increasing items produced by 1 would essentially result in $15 more being spent. So the rate of change in cost per item is, or in cost, I'll say in cost, is $15 per item. And we have to say this next part is very important. When 500 items are being produced. Now that's very important because the rate of change in cost changes depending on how many items are being produced. It's not the same for any X value. So you have to say that we're talking about when 500 items are being produced. So when this company has 500 items being produced, the rate of change in the cost would be $15 per item. So if they wanted to increase their production by 1 item, it would cost them $15 more. So you would use that number to make some decisions for your company if you work for them. Okay, and the last one is biology. The number of bacterial cells in a lab culture can be modeled by this function. It's a very common function to model populations, where T is measured in hours and P of T is measured in thousands of bacteria cells. Find the value of P prime of 1 to the nearest 10th and use a sentence to describe what it means. Okay, so first, before we can plug in the 1, we need to find the derivative. Now I'm going to write this in a different way to help you guys out. So here's my tip when you have a constant. So here's my original P of T. I don't like the quotient rule, so I like to avoid it as much as possible. So especially when you have just a constant in the numerator, what I like to do is I like to rewrite this like this, 100, 1 plus e. Now you don't have to do this, but I find it a lot easier. And then I don't have to use the quotient rule, and I simply have that constant multiple in front, so I can just ignore it. When I do the derivative of this, I have 100, and then I'll do the derivative of this part here. So I do have to do a chain rule. So the outer function is this power of -1. So the -1 comes down in front, and the power reduces by 1. So that's the outer part. And now we do the derivative of the inner part. The derivative of 1 is nothing. The derivative of e is a -t. That would be the -1, be the inner part, and then it would just be -t. So it's another chain rule there. Okay, so let's make that look a lot nicer. I'm going to multiply the -1s together. So we'd end up with 100, and I'll put the e to the -t here. And then I'll put this part down in the denominator again, 1 plus e to the -t all squared. Okay, now we're just going to plug in 1. So this is referring to 1 hour. So we're going to find P prime of 1. And this is something you would just plug into your calculator. You'll need to find the E button. Okay. Typically, I like to plug in the numerator first, get the answer, and then divide it by the denominator, just so you don't make any mistakes with that. Sometimes student, or I can make a mistake if I'm, okay, and then so I get negative 36. Now keep all the decimals in your calculator, but I'm not going to write them all out here. And then I'll divide it by 1 plus e to the negative 1 all squared. And you get negative 19.7. Is that right? Just going to double check the answer here, because I don't know if it's supposed to be negative or not, and if I made a mistake. Let's just double check. It's supposed to be positive, so I must have multiplied an extra negative 1 where I didn't need to. I had one there, and oh yeah, I did. I had 2 negative 1s, so they should have canceled it. Okay, perfect. So I'll just erase these negatives. Sorry about that, guys. Okay, great. So 19.7. So my intuition was calling there, because I thought the population should be increasing, so it should be a positive number. Okay, so we got 19.7. So this means, let's remember what our units are. So this is thousands of bacteria, cells. And then the unit of time here was, I think it was hours, wasn't it? Yeah, hours. So what this means in a sentence is after 1 hour, the population is increasing at a rate of 19.7 thousand cells per hour. Can squeeze that sentence in there. So each hour, and it's really important you say after 1 hour, because we plugged in 1 here for 1 hour. Every hour it's going to change. Okay. So now it says find the values of P prime of 2 and P prime of 3. Is the bacteria culture increasing or decreasing? Do you think the growth rate is increasing or decreasing? Why might that be? Okay, so I'm going to save you the time and just tell you what these are. So P prime of 2, if you plug it in, you can double check me if you want. It's 10.5 thousand cells per hour. And P prime of 3, if you plug that in, it is 4.5 thousand cells per hour. So let's look at these numbers here. So at 1 second, or sorry, 1 hour, the rate of change in bacteria is 19,000-ish, almost 20,000 cells per hour. Then it goes down to 10.5, and then it goes down to 4.5. Now, the rate is decreasing, but because these are all positive numbers, that means overall, the population is still increasing. So the population is going up, but it's just not going up as fast over time. And some reasons for that could be, look at this, I mean, there's a picture of a petri dish here. So probably there is limited space and resources for these bacteria cells to grow. So as the population gets bigger, they run out of room. They don't grow as quickly as they do at the beginning when there's lots of food and lots of space for these cells to grow. So that's probably why this is happening. The rate, we'll say the rate of growth, but the rate of growth is decreasing due to maybe space or food or whatever the bacterial cells need to grow. Maybe that is being used up. Okay, so that's it. In the assignments, you'll see some similar applications: biology, economics, and physics. All right, so I'm going to shut off the lesson now.